And yes, I'm a second-year PhD student within the block class lab, working with integrating post-quantum cryptography and homomorphic encryption within cellular medical IoT networks. And today we're going to be talking about evaluating post-quantum cryptography system and networking performance using the PQC-LEO framework. So we'll start off by outlining what we're going to talk about today. So we're going to start off with some initial kind of background on the deployment challenges of post-quantum cryptography, why an evaluation framework is still needed and important within research, an overview of the PQC-LEO's framework's functionality and its capabilities, a demonstration of the types of data and the functions that we can receive from the framework, and then an outline of what the next steps are and what we hope to integrate going forward. So we'll start off by setting off the context for deployment challenges. Massive progress has been made within the standardization process of post-quantum cryptography, with NIST, for example, completing its main competition and selecting several algorithms for standardization, alongside running in conjunction with that an additional signatures competition where they're reviewing proposals for extra additional signature schemes to standardize. So progress has been made, which is good, but there's still challenges when it comes to integrating post-quantum cryptography, particularly within resource-constrained environments such as IoT. The nature of the devices themselves, with very limited computational and energy storage capacity, can make integrating post-quantum schemes a bit challenging, especially with subsignatures or key encapsulation mechanisms having larger signature sizes, increased complexity, and larger subset sizes, which is difficult to bring into these very tiny devices. So in order to ensure the security of these networks going forward in the age of the quantum threat, a lot of research still needs to be done to understand what the best approach is and how we can effectively integrate these algorithms securely and effectively within these types of networks. So why do we need an evaluation framework? Within research, especially when we're talking about the performance of post-quantum cryptography, there are extensive tools that are used, most notably from the Open Quantum Safe project, specifically their libOQS and OQS provider libraries. And as of recently as well, within version 3.5 of OpenSSL, we're now able to test and utilize PQC directly within OpenSSL itself. The problem with these tools is, whilst providing a full set of PQC implementations, to be able to effectively use them within research and within different kind of experimentation setups, it often requires a lot of manual setup and configuration and setting up scripting so that everything behaves and everything works, which is a massive overhead for researchers and can also it can provide a barrier to entry, especially for new people coming into the field who want to understand the deployment challenges or the requirements of PQC. It also makes it kind of difficult to scale as well within experimentation. If you're having to constantly set up bit by bit, making everything niche and specific to what you're trying to do. Various frameworks have been proposed to try and help address some of these challenges, but they themselves also come with their own limitations, with the most often being either outdated implementations of the OQS libraries or limited functionality and what type of networking performance testing they can run. So to be able to kind of effectively do this, we need to try and not only address limitations of using these tools, but also the frameworks themselves. So this is where we introduce PQC-LEO. The main goal of this evaluation framework is to integrate those crucial and very commonly used PQC libraries within a framework that removes the need for manual setup or configuration, that will help guide the user through setting up the environment, running the testing, getting the data back out, so they can begin to kind of see what it is they need to do to be able to bring PQC within their systems. And it's also to provide a comprehensive set of testing types, so we can understand the real world deployments. So it's nice to have computational data in front of us and seeing how much CPU, etc. it needs, but we also want to see how it performs within networks, how it performs within networking protocols. So this is the kind of goal for the PQC-LEO framework. So give an overview of the functionality and what sort of testing and how it works essentially. So the framework is modular and it's open source. This is available for anyone to use. There's a link there for the repository. It's fully automated through setup, testing, execution, and result parsing. It will handle pulling in all the system dependencies that are needed, setting up the libraries, compiling, configuring, and when it comes to testing, fully running it, and when it comes to getting all the raw data out, putting it into nice CSV format so that we can start looking at the data, analyzing it. It provides various forms of customization for researchers to be able to configure the experimentation setup. So in terms of what algorithms are enabled within the LibOQS or OQS provider, what the delay control signaling, these are things that kind of allow it to fine tune so that you're not just you're able to make it work for your setup. It is supported on both x86 and ARM CPU architectures, with it currently being supported within Debian-based operating systems. Future goals of the framework will be to expand that out beyond Debian-based within all our Linux distributions, Windows, macOS, etc. So this is a kind of overview graph of the various types of performance testing the framework supports. And there's two main forms of categories of testing. We have computational performance testing and TLS performance testing, which has its own subcategories there. So we will start off with the computational performance testing. The framework utilizes the libOQS library for this, and we're able to evaluate PQC, chem, and digital signature algorithms that are supported by that library. And then with the tools within it, we're able to collect information on CPU and memory demands of the schemes to understand what challenges we need to consider when implementing these. The process, again, fully automated. It will take in the experimentation parameters, it will run and execute the testing, and it will output for you to be able to look at. So we'll start off by looking specifically at the CPU performance. The framework uses the SpeedChem and SpeedSig tools within libOQS to do this. These tools work by operating each algorithm and its respective cryptographic operations as many times as possible within a 3-second window. It will then capture metrics such as the CPU cycles and execution time during this window. So we're then able to see how effective the schemes are on that system. We're looking at memory performance, and this uses the libOQS testchem and testsigmem tools. And basically what this is you will supply your algorithm and the cryptographic operation you would like to test. It will run this once, and it will just that will finish. What we're then able to do is run that under the Valgrind memory profiling tool, which will capture the peak memory usage during that program's execution. So we're then able to see when we're executing this algorithm and its operation, for example, like key generation, we're able to see exactly how much memory, well, the maximum amount of memory that the program required, which is very useful when we're talking about deploying it within IoT devices that might have kilobytes of RAM. Again, the framework automates this process. If you were to do this by yourself, you would have to manually enter in bit by bit by bit. So the framework does all of this for you. It will supply, iterate, go through every possible combination, get that data, capture it, store it. Now, if we were to look at the TLS performance testing, and this category looks at understanding the performance of PQC, hybrid PQC, when integrated into the TLS 1.3 protocol. We also capture information for select classical schemes as well to provide a baseline, so we can compare the performance of these schemes against previous techniques. The framework utilizes PQC implementations natively supported within OpenSSL, the ones that have been standardized, such as MLChem and MLDSA, and it also utilizes PQC implementations added into OpenSSL through the Open Quantum Safe OKS provider library. The framework here will, again, automate certificate generation for the testing. It will set up machine roles and take in IP addresses and parameters, and it will coordinate the testing throughout. The framework supports both localhost testing and network testing, and this is a limitation often seen in other similar frameworks where only localhost testing is supported. With this, we're able to network devices physically or virtually if we're talking about cloud environments, and we're able to then account for real-world deployments of cryptography we're to use like wireless communications. We can test that out now instead of just doing it entirely within the local host. So we look at TLS handshake performance to start with. So many subcategories. This again looks at establishment efficiency for post-conflict photography, hybrid post-conflict photography within TLS. So the framework utilizes the OpenSSL, S-Server, and S-Time tool. What the automation will do is it will look through every possible combination of a digital signature and chem algorithm for both PQC and hybrid PQC. It will run an S-Server instance of that, and then we'll have a client on an S-Time. This will then run as many connections, TLS handshakes as possible within a defined testing window. And then from there, we're able to see how efficient we are and how many handshakes we can do within that time. The biggest kind of selling point of the framework in this type of testing is the automated coordination. When we have two physically separate devices, we need to be able to coordinate the testing between the two, which current combination we're on, if there's any failures or retries that we need to do, when to start and stop, etc. And this is all handled by the framework itself. The user is literally just all they have to do at this point is set up the devices, copy over the certificates, and press run and wait. And it will eventually kind of bring out that data as well. So it removes kind of the complications of testing this environment. This TLS speed testing, the final category, subcategory of testing. This measures the throughput of PQC and hybrid PQC operations within OpenSSL. This uses the OpenSSL speed tool. And basically what this will do is it will perform, again, as many operations as it can within a set time window. We're able to see how much, how many operations we can get through in that time. This complements the computational performance testing in the sense that when we use the SB tool, we're also accounting for the overhead of the OpenSSL library on the system. So we're able to kind of see, for example, if we were a server, how many connections we can get through in a second by running this tool, this test window, we can see how much can be done. So a demonstration of the framework's kind of capabilities and the results that we can get. As much as I would love to, it would be impossible to go through all of the different all the data that we can gather and all the results that we can get. Especially when it comes to TLS handshake testing, there's a lot of combinations that you can do. But what we can do is kind of show what how the framework will help guide you set up and kind of get the testing running. And we can also see examples of the type of data that we as researchers can get from using the tool. So the results that we'll show in the next set of slides, where we performed a proof of concept on both x86 and ARM architectures, and used version 0.4 of the PQC-LEO framework to do this. To highlight the automated setup features of the framework, a very minimal OS install was done. So in setting up the operating system, doing the very basic editing, and this highlights how the framework is able to pull in all the dependencies it needs and set up the environment entirely by itself. To highlight the supported customization options as well, within this experimentation, we supplied customization flags to the setup process to enable algorithms that are disabled by default in OpenSSL, OKS provider. And again, to highlight the coordination automation of the framework, testing was done using physically networked devices connected via a switch. So to start off with, as an example of how the framework can help minimize the barrier of entry for researchers trying to get into post-quantum photography. Here we have an example of the setup script. Again, when you run this, it will provide you with the different types of testing options you set up. So you could set it up just to do computational performance testing. You could set up to do both that and networking performance testing. And it will ask, do you want to enable disabled algorithms, etc. So it'll help walk everyone through it. Here's an example of the TLS handshake, the networking performance testing. On the left-hand side, you would see what would be your server machine, and on the right-hand side, you would see what would be your client machine. When you start these scripts, it will ask, will this be a server, will this be a client? It will ask you for the number of test runs, IP addresses. It will check to make sure that you've generated the certificates that will be used within the testing. And again, on the client side, it will ask, how long should we run these testings for? It makes the process really, really simple and easy to use. And there's extensive manuals and documentation that's also been written for the framework as well that people can refer to really, get in a bit easier. So if we start looking at some of the examples that the framework can provide for us in terms of data, we have here an example of CPU performance. On the left-hand side, we have an x86 system. On the right, we have an ARM system. This shows us the average operation time for each algorithm. These are for chem algorithms here. And then from here, we're able to, it's set on a logarithmic scale as well. From here, we're able to start comparing the performance of each of these schemes, and we can see how they vary on system architectures, and what we need to consider when we're talking about IoT deployments, for example. Here's an example of some of the memory data that we can gather. And this is specifically on x86 machine for chem algorithms. And from here, we can see the memory usage for each type of operation. So for key generation, encapsulation, and decapsulation. And we can see specifically the type of memory as well. So how much heap memory was used, how much stack memory was used. We can, at the very peak of the program's execution. So we can see exactly how much we need, how much memory headroom we need to be able to operate these schemes. Here is an example of the TLS handshake performance testing. So these results here have been filtered to top 10, mainly because again, it's a lot of combinations. But from on the top row, we have x86 PQC and hybrid PQC, and on the bottom we have ARM PQC and hybrid PQC. And what's showing us here is the total number of TLS handshake connections within real time. So during the 30-second testing window, we're able to see how many connections could be done for each combination of digital signature and key encapsulation mechanism. This is quite useful as well, because we're not only just accounting for how much time the CPU is specifically working on it, but we're able to account for all of the overhead of the system for sending packets over, etc. So we can start to see the demands here. And then finally, here is an example of the TLS speed results. What this is showing us here is the number of operations that could be done within that time window. So for example, if we were to look at the left-hand side here, where it's x86 PQC chem, we see for ML chem 1024, the number of decapsulations that can be done a second, the number of encapsulations that can be done a second. So we can understand how much data we're able to start to deal with. This is the speed we can deal with. So finally, the future steps for the framework. So the main goal is to ensure that the framework consistently provides the most up-to-date implementations of post-PQC schemes that are available. For example, OpenSSL 3.6 will be coming out in the next couple of weeks. We hope to integrate that within the framework, and just make sure that the researchers are able to easily have the most up-to-date information. And again, expanding operating system support beyond Debian-based systems to help kind of make it a bit easier for everyone to use it. And then finally, one of the most important things for IoT is the energy consumption. We aim to start integrating automated measurement of energy consumption. This will provide us very useful information on the demands that post-quantum cryptography would have for IoT. When we start looking at the computational performance compared to classical schemes, there's often times where some PQC schemes will perform better than classical. But when it comes to IoT, energy is the biggest, especially when it comes to network transmissions. If we have larger signature sizes, we have to transmit more, which requires more energy. So we need to understand how much we're losing here when we start integrating post-quantum cryptography into IoT. And that is it.